Welcome to the continuation of the lecture on the non-radiating dielectric guide. We had been discussing about the characteristics of the LSM mode. Let us go to the characteristics or the field profile of the LSE mode. So, if we draw the NRD again in order to illustrate the LSE mode, the LSE mode, the E field of the LSE mode. So, this is the LSE 01 mode. So, the E field of the LSE 01 mode would be just different style here. So, let me call this the electric field. So, this is the electric field profile of the LSE 01 mode as far as the magnetic field profile goes. So, this is the magnetic field profile. This is the magnetic field profile of the LSE 01 mode. So, you can see that let me just draw the axis, draw the axis. Okay. So, if we just see that the electric field is totally tangential to the air dielectric interface. So, this is the LSE 01 mode. Okay. So, this is the lowest eigen number, this is the lowest eigen number along this direction, and this is there is a half wavelength variation in this direction. So, that is what this 1 suggests, the half wavelength variation along this direction. So, we see that in a nutshell the LSM 01 mode, the principal property of the LSM 01 mode, it is the absence of the magnetic field component normal to the air dielectric interface, which we are seeing here. So, the magnetic field is entirely tangential to the air dielectric interface, while for the LSA 01 mode no component of the electric field exists normal to the air dielectric interface. The same, there is the electric field is completely tangential to the air dielectric interface. There is no normal component of the electric field to the air dielectric interface. So, it can also be seen that the configuration of the LSM 01 mode, if you look at go back to the LSM 01 mode, its configuration closely resembles that of the dominant TE 01 mode of the rectangular waveguide. Why we say that is that, as we said, that if I have a rectangular waveguide, its dominant mode will have a configuration like this. So, the electric field will be like this. So, you see that this electric field matches in direction with that electric field. So, therefore, we say that the rectangular waveguide dominant mode or the TE01 mode, the field configuration of that mode matches that with that of the LSM 01 mode. As we also discussed that the low loss nature of the NRD is fundamentally due to the field profiles of its modes. Okay, because the LSM 01 mode field profile, the magnetic field is normal to the metallic plates. So, a reduced electric current in the metallic plates, whereas if you look at the LSE, if you look at the LSE 01 mode, the magnetic field is along the metallic plates, it is tangential, it is more tangential to the metallic plates. So, there will be currents induced in the metallic plates leading to loss. So, therefore, the LSC's modes are more lossy than the LSM modes. So, therefore, the low loss nature of the NRD in the most often used mode, which is the LSM mode, it is fundamentally due to the field profiles of its modes, and also, so there are two important conditions for the low loss nature. One is the field profile of its modes, and number two, the distance between the ground planes being less than the half of free space wavelength. So, this distance being less than half of free space wavelength. So, these are the two fundamental reasons why the NRD is less lossy, is a very low loss guided structure compared to other structures or even other very similar structures like the H guide. Okay. So, if I arrange the modes, in so, if I arrange the modes of the NRD in ascending order, the lowest one will be the LSE 00 mode. So, this is frequency hertz, okay, which has a 0 cutoff frequency. Okay. So, it essentially has it would propagate a DC, followed by the LSE 01 mode, which is the next higher order mode, and then followed by the LSM 01 mode, which is the next higher order modes, and then will come the other higher order NRD modes. So, you see, if we are preferentially using the LSM 01 mode because of its low loss, we have to very well appreciate that there are two modes, LSE 00 and LSE 01, which have a lower cutoff than the LSM 01, and therefore, these two modes will have a tendency to get generated at any kind of discontinuity, surface imperfections of the NRD, curved sections and the like. Okay. So, this must be very carefully borne in mind, the clear difference between the rectangular waveguide situation where we are using the dominant mode and the NRD guide where we are constrained to use a lower loss mode with a higher cutoff frequency. So, therefore, the other two modes which are preceding to that, they have a tendency to get excited at any kind of discontinuity or curved sections, and this has to be taken into account. And as we said, that if that is not permissible, then we have to use components like mode suppressors in order to suppress the LSE 01 mode or the LSE 00 mode. Now, how do we just principally how do we use the mode suppressor? For example, if we have to use the mode suppressor, we have to look at the field profiles of the LSM 01 mode. You see that the field profile of the LSM 01 mode is the electric field along the ground plane. So, if we insert again, if we just mark the axis. So, this is y and this is x. So, if we insert a metallic plate ideally along the YZ plane, that is principally not going to affect the electric field because it is normal to the metallic plates. So, that is not going to affect the electric field. However, if I insert a metallic, so this is y and this is x, if I insert a metallic plate along the YZ plane, that is going to short out these electric fields because these are tangential, they would be tangential to the metallic plates, and therefore, that is going to prevent the LSE 01 mode from getting propagated. But there are a lot to the design of such mode suppressors other than just shorting out the electric field. There are bandwidth issues, there are many other issues, and like the design of such mode suppressors or any mode suppressor is a very challenging research topic on its own. Okay. The other thing which should be borne in mind is that if you consider the LSM01 mode, and if you say that if I insert a mode suppressor along the YZ plane, nothing is going to happen to the LSM01 mode, it is not principally correct, because you see that the magnetic field is along the YZ plane. So, if I insert a metallic plate, okay, or typically it happens like a corrugated plate kind of thing with a structure like this. So, okay, a structure like this, a corrugated type plate. Okay. So, this is an example or a typical picture of a mode suppressor, and this will be inserted if this is the y and that is the z direction. Okay. So, if I insert this kind of a structure on the YZ plane, you appreciate that the magnetic field which is along the YZ plane, because it is the LSM01. So, the magnetic field is along the YZ plane, it is tangential to this ground plane, and therefore, currents are going to be induced on this surface, and therefore, that is going to increase the loss. In fact, that we have to deal, we have to also see what is the polarization of such currents and how they interfere with the mode propagation. So, please bear in mind that the design of a mode suppressor has to take into account many factors, including loss, including bandwidth, including how well it suppresses the undesired modes, and like a lot of such factors which are going to be relevant in the suppression of the undesired mode and in the propagation of the desired mode, but the desired mode is not going to be totally unaffected by the insertion of the mode suppressor. This has to be carefully borne in mind. Okay. So, now that we have a picture, so now that we have a physical picture of the NRD, its hybrid modes, its essential difference between the rectangular waveguide and such guided wave structure, both in terms of advantages, disadvantages, modal characteristics, use of the non-dominant mode and things like that. Let us come to a more mathematical description or the analysis of the NRD. So, the analysis of the NRD at this point is not a very difficult job. The reason why I tell it is not a difficult job is that we have already studied other kinds of mode functions, because you see that the modes in the NRD, if I say they are the LSM01 or the LSE01, the LSM01 is characterized by no magnetic field along the x direction. So, that is, therefore, I can say this is a TM to x mode. It is transverse magnetic to x. It is a TM to x mode. There is no magnetic field along the x direction. We have made this mode before. We have even written down the potential functions of this x. So, the LSM01 mode is nothing. It is nothing but the same as the TM to x mode, which is given by the mathematical description of such fields are given by A equal to ux psi. Similarly, the LSE01 mode, or the LSE modes, I should not say 01, the LSE modes are a general class of TE to x modes, because there is no electric field along the x direction. The electric field is totally confined in the YZ plane. So, it is a TE to x mode, it is the other name for a TE to x mode. We have already made this TE to x mode before, we have already written down its field distribution from the potential function. So, once the potential function is given, we can write down the field distribution. So, let us see how we can use the knowledge earned in our previous lectures in order to understand the foundation in which or I should say in order to understand the mathematical foundations of the NRD modes, how the NRD modes can be expressed mathematically. So, let us go to the LSM even modes. We said that LSM even modes are characterized by the potential function having an even distribution or a cosinusoidal distribution along the width, which was along the x direction. So, in the dielectric region, let us draw a mini picture here, so that we can relate the picture with the fields. Let us draw a mini picture here, so we can relate the fields with the diagram once again. So, this is my A, this is my this is my B, this is my Y, this is my X, and this dielectric constant is epsilon r, and A is less than lambda 0 by 2. Region 1, region 2, region 3. So, for the LSM even modes, we have a cosinusoidal distribution of the potential function here. So, in the dielectric region, which is essentially mod x less than or equal to b by 2, we can all appreciate that. So, mod x is less than or equal to b by 2. The psi function is given by ADE cos q m e x sin n pi y by a e to the power minus j k z e z. This is the function. D refers to the dielectric. D refers to the dielectric, E refers to the mode being even, this is the even mode with a cos variation, this is the eigen number inside the dielectric slab in the dielectric region QME. Sin n pi y by a denotes the reflection, as in it is not a new term to us, we have encountered this in the rectangular waveguide. So, this models the reflection in the y direction. Okay. So, because of the presence of, we already know how to choose this sign and why it is not cos, we have already done that exercise in the rectangular waveguide in order to preserve the characteristics that the tangential electric field has to be 0 on the on the ground plane. And this is this denotes the propagation along the z direction. E refers to the even mode. Okay. So, this is the nomenclature of the LSM even mode in the dielectric region. In the air region, mod x greater than equal to b by 2, and we have psi is equal to a e exponential minus p m e mod x minus p by 2 . sin n pi y by a e to the power minus j k z e z. So, here A refers to the air region, which is mod x greater than b by 2, which is region 1, you can appreciate, because mod x is greater than b by 2. So, that is refers to region 1, this refers to region 2, this psi in the dielectric region refers to region 2. So, we are now in region 1. So, A refers to this subscript refers to the air region, E refers to the even mode, because we had started with the even mode here. Okay. So, in order to describe the variation of the fields along the x direction, it is evanescent that the waves are decaying down along the x direction. Okay. So, in order to describe that behavior, minus p m e, it is the eigen number along the it is the eigen number in the air region, mod x minus b by 2, because the decaying starts from here. Okay. So, at mod x equal to b by 2, it is exponential 0. So, it is 1. So, the decaying starts from here, and again this there is nothing happening along the y direction. So, the y direction variation of the fields is unaffected. So, it is the same as this, and again there is nothing happening along the z direction. So, that z direction variation of this wave number will be the same as the dielectric region. Okay, because the phase has to match along the air dielectric interface, otherwise we cannot match the fields. So, this is called the phase matching condition. So, the phase here and the phase here along the tangential phase has to match, otherwise we cannot match the fields in the air dielectric region. So, this is a very important condition called the phase matching condition. Okay. So, the concept is illustrated. Now, we come to the LSM odd modes. For the LSM odd modes, in the dielectric region, mod x less than equal to b by 2, we have psi is equal to a d o, O standing for odd, sin q m o x sin n pi y by a e to the power minus j k z o z. So, again d stands for dielectric, O stands for odd. We have now the sign variation, okay, because we are dealing with the odd mode. Therefore, it is a odd variation with respect to x inside the dielectric region. This stays as it is. It satisfies the fact that the tangential electric field has to vanish on the two ground planes, and then we have this O k z o z standing for the fact that it is a propagation constant along the z direction for the odd mode. So, this ends the nomenclature in the dielectric region. In the air region, so, please note here in this case that the air region, in the air region mod x greater than or equal to b by 2 refer to both the region 1 and region 3, because for both the cases mod x is greater than b by 2, okay, because mod x is positive. So, it is greater than b by 2. So, it refers to both region 1 and region 3. Okay. So, in this case however, in the AR region which is mod x greater than b by 2, psi is equal to AAO exponential minus PMO mod x minus b by 2 in the AR region which is mod x greater than or equal to b by 2, we have psi is equal to AA0 exponential minus PM0 mod x minus b by 2 sine of n pi y by a e to the power minus j k z naught z for x greater than or equal to b by 2, which in this figure is region 1, x greater than or equal to b by 2, and psi is equal to minus A0 exponential minus PM0 mod x minus b by 2 sine n pi y by a e to the power minus j k z 0 z for x less than or equal to minus b by 2. So, x less than or equal to minus b by 2 is region 3. So, we have the two forms of the potential function. For mod x, we have the two forms of the potential function for x greater than or equal to b by 2 and x less than or equal to minus b by 2. Okay, so, this is necessary in order to match the fields for the odd mode, match the fields for the odd mode on the region 1 and on the region 3, the air dielectric interface on the region 1 and the air dielectric interface on region 3, and to describe the variation of the fields in the region 1 and region 3 for the odd mode. Okay. Okay, so, this you can clearly see by after writing the expressions for the electric and magnetic fields for the odd mode, as to why this has to be expressed in two different ways for the odd mode and in one concise form for the even mode. So, in the above QME, so in the above or in the above expressions QME, PME, QMO, PMO are the eigenvalues of the characteristic equation for the LSM even and odd modes. We already said that the subscript E refers to the even mode and the subscript O refers to the odd mode. So, this subscript O, it refers to the odd mode. Also present in the propagation constant Kz. All these terms which are present here A, D, E, A, E, A, D, O, A, O, they refer to the amplitude terms of the potential functions. Okay. So, let us stop here for this and we will continue from here.